So could it be that is a scalar and weight is a vector?
But that's not really the definition of either, right? But that is a difference. Mass is the amount of matter contained in a specified volume. Whereas weight is the force of attraction of the Earth on the mass. And you can then obviously state what you stated at the end, that mass is actually a scalar, and therefore weight is actually a vector. Mars has a mass of 6.4 times 10 to the 23 kilograms, and its moon Phobos has a mass of 9.6 times 10 to the 15 kilograms. If the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15 newtons, calculate, now this is a very vague question, huh? Calculate how far apart Mars and Phobos are. It should state after that with respect to their centers. Because when we're calculating that distance of separation, we're calculating it from the center of Phobos to the center of Mars. Also, what I want you to note here, unlike the other questions we actually came across, here they didn't give you the radius of Phobos or they didn't give you the radius of Mars for you to actually do a calculation. Somebody's got their mic on, please. You don't mind putting it off? It's somebody that came in pretty late. Thank you. So we're going to assume that it's from the center to the center. Now, because some of you have either starting with this or when we did our first lesson, you hadn't done this at all, it's going to be F equals to G M1 M2 over R squared. The other thing is I'm going to actually go ahead and I'm going to do Coulomb's law this weekend. I think with the most of y'all, I'm going to just stop there at Coulomb's law. If you've done electric fields and you're going to get tested on it, that small part over there, I think we're going to actually just allow you to actually complete that with your educator. It's quite simply because I still need to do quite a bit of revision on all of this before you actually write your paper on Friday as well. And I think many of you are writing on Friday. Right, so they gave us the force. 4.6 times 10 to the 15 newtons. The value of G, 6.67 times 10 to the minus 11. The mass of Mars, 6.4 times 10 to the 23. The mass of Phobos, which is one of the moons, 9.6 times 10 to the 15. Over R squared. What I've noticed is that there are many learners that don't have the newer calculators. So for you, I'm actually going to do the long approach and actually calculate R. I'm going to take r squared up to this side. I'm going to bring down 4.6 times 10 to the 15 here. And I'm going to get r squared is equal to 6.67 times 10 to the minus 11, 6.4 times 10 to the 23, 9.6 times 10 to the 15 over the force 4.6 times 10 to the 15. And because I want to find r, I'm going to square root the right-hand side now. Somebody can assist me with the calculator work, or you've already done it. Please try and give it in scientific notation if it's a large number. Anyone? Please, guys, we need to work a little bit faster if you can give me the answer.
So it's 9,44 times 10 to the 6.
Anybody else got that? That sounds good. Right. Calculate the weight of an astronaut whose mass is 72 kilograms on Phobos if the radius of Phobos is 7.4 times 10 to the 6 meters. Let me explain this question by drawing a little diagram there. I'm going to do this on the next page. So you've got Phobos here, and you want to find out what is the weight of an astronaut that's placed on the surface of Phobos. To find out the weight of the astronaut, you need the mass of Phobos, which is going to be your M1. And they did give us the mass of Phobos. They gave it to us in the previous question. The mass of Phobos was 9.6 times 10 to the 15. They gave us the mass of the man, 72 kilograms. They gave us the radius of Phobos because it's going to be from the center of Phobos to where the man is located. Now, somebody asked me, why don't we take the distance from the surface of Phobos to the center of the man? Because that distance there is so small compared to the radius of Phobos, we ignore it. It's literally only going to be about a meter at most, on average. And that 1 meter is going to not play a huge role in the force because it is exceptionally small compared to here, 7,400,000 meters. So 7.4 times 10 to the 6 is the distance of separation. So the question said, what is the weight of the man? The weight is the force with which Phobos is going to pull the man down. And that force is your gravitational force given by this equation again. So they tested it twice. Interesting. They really don't do that. 6.67, 10 to the minus 11. 72 is the first mass. 9.6 times 10 to the 15 is the second mass. And 7.4 times 10 to the 6 is the radius of Phobos squared. the answer? It shouldn't be very large. I'm guessing something like 500 newtons, maybe even less. Let's see what's the mass of Phobos. Oh, much less. Yo, actually, 10 to the minus something.
I saw.
Yes, sir.
If I'm not wrong, I think it's 8.42 times 10 to the negative 7.
Yeah, something like that. True.
Yeah.
Thank you, sir. Right, and we're done with that one. There are two more questions here. I want to do this one here. Somebody actually asked me about this, and I'd rather prove it here now. Right, it says a man of mass 70 kilograms is on the surface of the earth. So we've got a man on the surface of the earth. Earth, man. Again, we know that Newton's law of universal gravitation is definitely coming out. Please ensure that you learn it. Somebody in grade 12 has taken the liberty of writing out all the definitions for Newton's laws for you guys. The definitions that are not there as yet are the ones on electrostatics and vectors. But I'm going to put up these definitions for you so that you can actually have them. This is quite unique because here they are asking you to prove the equation for the acceleration due to gravity. Well, in this case here, on our planet, which is Earth, because m subscript e is the mass of Earth there. So for those of you that have forgotten how to do this, here's a recap. If you had to calculate the gravitational force that the Earth exerts on the man, we can use two formulae. That gravitational force there is given by the very simple formula that you used during your calculations in Newton 1 and Newton 2. That m over there is the mass of this man, which I'm going to call the mass of an object. It doesn't have to be the man. It could be any object that's placed close to the surface of the Earth. So I'm going to call that MO. This same gravitational force, which is also now interpreted as the force between mass 1, which is the mass of the Earth, and mass 2, mass of the man, and the distance of separation between them is the radius of the Earth. So that same Fg can be given by G m1 m2 over r squared, where m1 now is the mass of the Earth, m2 is the mass of any object placed close to the Earth, and r is technically the radius of the Earth here. I'm putting the e down so you know it deals with the Earth. But it doesn't have to be specifically for Earth, eh? It could be for any planet. In other words, you can replace the e with just p, where p represents the mass of a planet and rp would be the radius of that planet. Now, those two formulae are the same. This Fg formula here And this FG formula there is the same. So equation 1 here is equal to equation 2 here. Which means M, yes, sir?
So can we only use the first equation if the object is on the Earth's surface?
Very good. Or very close to the Earth's surface. Right? And 99% of the time when they are testing this as a proof, they will tell you that the object that is in question is very close to the surface of the Earth. Any other questions?
No, sir.
Okay. So MO times G equals to G, mass of the Earth, mass of the object placed close to the Earth, over R squared. So MO goes off on both sides. So you're going to end up with G equals G times mass of the Earth, technically over the radius of the Earth squared. And there's the proof over there. It looks very, very easy compared to some of the other hectic ones we did. So you can quite easily commit this to memory. My suggestion is please do this. Calculate the acceleration due to gravity if the man is now on the surface of a planet 4 times that of the Earth, but with the same radius. Now, I can't remember which year I took this out from, but you can be guaranteed that the mass of the Earth is going to be given to you in your data sheet. And the radius of the Earth is also given to you on your data sheet. So if I'm lucky and I have the paper here, I can go straight to my paper and double check that the mass of the Earth is 5.98 times 10 to the 24, and the radius of the Earth is 6.38 times 10 to the 6. Right? It will be on your data sheet, so please look for this. Now, learners sometimes don't know that it is actually on your data sheet. So look for these constants because they will be provided for you, and please use them. So 6.3 is now asking us to calculate the acceleration due to gravity on a new planet, which has a mass 4 times that of Earth and the radius exactly the same as Earth. Now, if it has a mass 4 times of Earth and the radius equal to whatever we have, then by all intents and all calculations, it should just be 4 times 9.8. And 4 times 9.8 is 39.2. So I'm hoping that the acceleration due to gravity on this planet is exactly 39.2 meters per second squared. All right, let's see if we write. So G, 6.67 times 10 to the minus 11, 4 times the mass of the Earth. So 4 times 5.98 times 10 to the 24 divided by the radius. Note they said, but with the same radius of the Earth, 6.38 times 10 to the 6. And I said that the answer should be about 39.2 meters per second squared.
So,
Mm-hmm.
so though, is that a 5 next to the 4 times 5?
But if you're
Did you
telling me,
intend to put the 5 there?
what do you mean intend to put the 5? This is 4 times the mass of the Earth. This is the mass of the Earth, sir. There. So it's 4 times 5.98 times 10 to the 24.
Sorry, sir.
So I'm going to write my answer down. Let's see how close I came to the correct answer. Anyone?
So it's 39,20.
Thank you.
Sir,
39,220 meters per second squared. Did they say magnitude or they said acceleration? Your acceleration due to gravity on any planet, as far as we know, is going to be towards the surface of the planet. Or you could just say downwards. Right. Now comes the next one. How will the answer in 5.3 change if a man of 50 kilograms was on the planet? So we change the mass of the man from 70 kilograms down to 50 kilograms. How will the acceleration on the planet change if we change the mass of the man himself? Increase, decrease, or remain the same? I'm going to allow you to give me the answer to that.
So wouldn't it increase because mass and acceleration are inversely proportional?
Everybody would actually think that, weirdly. But here is the formula for the acceleration due to gravity on any planet. And if you look very carefully, this acceleration due to gravity is directly proportional to the mass of the planet. Mass of the planet, not mass of the person on the planet, just the mass of the planet itself. So your G is directly proportional to the mass of the planet. The same G is inversely proportional to the square of the distance from the center of the planet. What does that mean about the mass of the man placed on the planet? He won't affect the acceleration due to gravity on the planet, because the acceleration due to gravity on the planet is not dependent on any object that you place on the surface of the planet. It's only dependent on the mass of the planet and the radius of that planet.
Sir,
Yes, sir.
so in the acceleration formula, the mass of the object is not present.
No. I know what you may be thinking, but what if I drop a feather and a steel ball? They won't have the same acceleration. This formula here is taking into account that there are no external forces acting on the object. In other words, we eliminate air resistance. The only reason why the feather takes longer to land on the ground is because it actually experiences more air resistance than the ball itself. But if we remove air resistance, you can actually watch the video for this, right? Both of them would actually reach the ground at exactly the same time. There would be absolutely no difference between the two.
Sir,
Yes, sir.
so in the test, they will have to state whether there is air resistance or not.
No, they won't. Because we don't take any, so all our calculations for Newton's law of universal gravitation is in the absence of air resistance, sir.
Thank you, sir.
Right. Now, this formula here is not as popular as the other one, the F equals G m1 m2 over r squared. But please don't think that it can't come out here. The entire question was based on this. Right, somebody just join. If you just wouldn't mind muting your mic, please. Thank you. This looks interesting. Because somewhere in this question it says do not use scientific notation, which means we're going to be dealing with very accurate values that we're going to be using here. Right, please read. I'll be back in a minute. Just excuse me.
I was stopped.
All right, let's start. All right, let's see what we got here. It says the International Space Station was launched on 20th November 1998. It has a mass of 4,197,250 kilograms. Astronauts, wrong spelling, and food are taken to the International Space Station with the Soyuz capsule, which launches on the top of a Soyuz rocket. After the launch, the capsule and the rocket separate. The rocket part of the Soyuz returns to Earth. The Soyuz capsule keeps going to dock onto the space station. The mass of the Soyuz capsule is 2,900 kilograms. So, looks like we got these two masses here, which is the mass of the capsule, which is 2,900, and the mass of the ISS, International Space Station, which is 4,197,250 kilograms. That looks like it's M2. Right, this person has got a bit of a problem with the language. Define Newton's Universal law of gravitation, it's supposed to be. That's a theory question. Calculate how many kilometers above the Earth's surface the International Space Station is if it experiences a net force of 36,99 newtons to keep it in orbit. Sure. Do not use scientific notation for this answer. Do not use. Okay. I think what they meant was do not use scientific notation for that mass. But you can't but not use scientific notation for the mass of the Earth. Huh? How many kilometers above the Earth's surface? That is not an easy question. Anybody knows why? So here's the Earth. Here is your International Space Station. We are going to find out the distance from the center of the Earth to your space station there. We're going to find out what that R is there. And we need the mass of the Earth, which we already know. We can't but not write this in scientific notation. But the mass of that space station is 4197250. And we're going to work out R when the force on the space station has dropped to 36,99 newtons. That's a very small force, eh? Yo, imagine that. A huge space station like this ends up with a force of 36,99 newtons. Why? Because it is extremely far from the center of the Earth. What I want to emphasize again, when we work out the distance is going to include the radius of the Earth. That radius of the Earth alone, which is this blue bit here, .38 times 10 to the 6 meters. Okay, maybe even that we can get away with not using. Scientific notation. I'm going to try my best not to use it there. Let's see what happens though. But the mass of the Earth, we have to use it. Right, 4.2. Let's find out what R is. F equals to G M1 M2 over R squared. 36,99, 6.67 times 10 to the minus 11. Mass 1 is the Earth. Mass 2 is the International Space Station. 4,197,250. And we're going to divide that by R squared, which is the distance from the center of the Earth to ISS. So R is going to be the square root of that entire term on the right-hand side. 6.67 times 10 to the minus 11, 5.98 times 10 to the 24, 4,197,250 over 36.99. Anyone's got the answer for R? Because I'm guessing it's going to be about as big as this value, or just slightly bigger than that.
So you want the final answer in scientific notation?
No, no. Give it to me without scientific notation.
67275000864.
What do I feel that
Got
that's
the
wrong?
same thing, sir.
Okay. All right. So let's convert that to so that's in meters, right? So how high is it going to be above the surface of the Earth? So above the surface of the Earth, remember, to work out the distance from the surface of the Earth to where this satellite is, we have to take away the radius of the Earth, because what we've calculated is the entire distance, including the radius. So that's going to equal to 672.7500.864 minus 5.98 times 10 to the 6. What's the answer now?
672
Mm-hmm.
152 0864.
This is in meters. So in kilometers, you take this and divide it by 1,000 now.
So do you get penalized if you leave it in meters?
I think you would, because I think the question clearly said how many kilometers away. Okay. You'd lose a mark or two. Normally we leave it in meters. So we divide that by 1,000, what do we get? 672.1520. Am I right?
Yes, sir. Yes, sir. Comma 864.
Yo. 6,721,520 kilometers. Yo. That is high. And far away.
Oh, sir.
Can't be that far. So you think there's a problem with the answer over here?
Maybe the question is wrong.
Let's see what the answer was.
Class pools.
Yeah, you gave me the wrong answer. You're right. What did you tell me the answer was? No, it couldn't. How could it be wrong? But
So maybe it's the maths.
they got 638.0672.738. This answer here. Okay. We did everything else correctly. We subtracted the radius of the Earth. But you gave me a slightly different answer there.
So they use 6 times 10 to the minus 11, not 6,67.
It won't make such a huge difference.
So maybe the memo is wrong.
But here's the problem. Where they got this number from? This number here and that number there is not the same.
So the memo is wrong.
Yeah, the memo is way off. So yeah, they gave some horrible values there. Our
So
method's
I just
right.
rechecked
Unless
the
these
values, so they were all correct.
they're all correct. So there's something, yeah, there's probably something wrong with the way the question set out. Please don't use 6 times 10 to the minus 11, eh? It has to be 6.67 times 10 to the minus 11. Sorry, it's supposed
Yes,
to be
sir.
6 point, there's the mistake here. It's 6.38 times 10 to the 6. I don't think it'll make much of a difference though. What's the answer now?
Six, 7, 2,
Mm-hmm.
1, 1, 2, 0, 8, 6, 4.
You still won't get the same answer they got. We got a ridiculously large number. I'm just going to leave this there because these values are really, really very, very large.
So
Let's go on. Yes, sir.
is the answer 6 billion?
It looks like it's 6 million in terms of kilometers. Because if you put the decimal there, it'll be 6,721,120, 864 kilometers. And you're right, that's ridiculously large, isn't it? There's something amiss with the question. I think it's here. I think it's that. I don't think the gravitational force is so small on Soyuz. I think it's much larger than that. I think that's where they made their mistake.
Yes, sir.
36.99 newtons on a huge mass of almost 4.2 million kilograms. Anyway, let's go back. Let's answer the last couple here. The Soyuz capsule is now approaching the space station. Calculate the force between the space station and the capsule 200 meters apart. So that's going to be F equals to G M1 M2 over R squared, 6.67 times 10 to the minus 11. Soyuz was 4,197,250. And what was the space capsule mass? Okay, 2,900. And they are 200 meters apart. So 200 squared. Answer please for the force.
20,3 times 10 to the negative 6.
But they ask for the magnitude of the force. Calculate the force between them. So it'll be towards each other. Or you can just say attraction. The gravitational force is a good example of an attractive force. Then it says, how does the acceleration of the satellite change? Write down increase, decrease, or remain the same. As the satellite is approaching the space station, that distance of separation is going to continuously decrease, which means the net force on it is going to increase, which means from Newton's second law, the acceleration should increase. Why? Because as this moves closer, r gets smaller, the gravitational force is inversely proportional to the distance of separation. If F increases, then your acceleration will increase. So 4.4 increase, and then the explanation. F is inversely proportional to r squared. As r decreases, F increases.
Sir,
Yes, sir.
so in the test, will it be marked wrong if we don't write it out in words?
Yes, you will, sir. Please write it out in full sentences. All right, people. We're going to stop over here. I'm quite likely going to continue on Saturday based on the fact that many of you here are now not writing a common paper and you're writing an internal paper. I would like to know exactly where you're stopping, though, especially the DHS learners. Because if I don't have a definitive answer, I don't know where to stop at and how far to go down the line. Whether you're going to start Coulomb's law, you're not going to do it. But I think I'd rather just do it because there's a few people over here that are actually going to get tested on the whole thing. So I'll stop at Coulomb's law. All right, thanks for attending, everyone. We'll meet on Saturday at 6 p.m.
Thank you, sir.
Please, if you can, just get the scope for your paper, please.
Ah,
Thank you, sir.
All right, guys. See you.
sleep well, sir.
You too.
Good night.